Good. Let's get started. So it's a pleasure today to have Ramteen Sioshansi here. It's been a while that I really wanted to invite Ramteen. Finally. So thanks, Ramteen, for coming. So a bit about Ramteen. Ramteen is a professor at Department of Engineering and Public Policy, also at Department of Electrical and Computer Engineering at Carnegie Mellon University, CMU. Prior to joining CMU, Ramteen used to be a professor at Ohio State University. Ramteen's research focuses on integration of advanced energy technologies, renewable energy, storage, and transportation. If you are active in storage and market integration of storage, I'm sure that you will see a lot of great papers by Ramteen. Ramteen is an IEEE fellow, and he served 3 two-year terms on the Electricity Advisory Committee, a federal advisory committee to the U.S. Secretary of Energy. And Ramteen, you got your PhD at IEOR, Industrial Engineering and Operations Research at UC Berkeley with our good friend Shmuel back in 2007.
Yes, 2007.
Fantastic. So, Ramteen, the stage is yours. And just a second. Yep. Cool. Yeah. Sure. Screen. Good. Yes, please.
All right. Great. Well, thank you, Jalal, for the first of all, thank you for the invitation. Jalal and I have known each other. I don't even remember how many years it's been, but quite a long time, and we've seen each other at various conferences and workshops, but this was the first time that the timing worked out to visit DTU, so I really appreciate the invitation and the opportunity to present this work. So before I go into the presentation, let me just say that this is, so on paper, it's joint work with this PhD student, Shuyi Chen, and a colleague of mine in this Heinz College of Information Systems and Public Policy at CMU named Shixiang Zhu. But as is often the case with student work, this is really like 95% of the work was done by Shuyi, 10% of the work was done by Shixiang, and like negative 5% was done by me, meaning I was counterproductive to getting the work done. But nonetheless, I'm here taking credit for the work. So this really is Shuyi's work. And unfortunately, because I mean, obviously I'm happy to be here visiting Denmark, but because of the timing, I wasn't able to attend the Inform's annual meeting, which has been happening this week.
Actually, yes.
What's that?
It was the last 2 days, I guess. I guess today is the last day.
I think today is the last day,
Yeah.
yeah. But in any case, the only reason I mentioned that is because Shuyi won the Best Student Paper Award from the Energy, Natural Resources, Environment section of Inform. So he was, I think at this point, he has presented this in the award session. So unfortunately, I wasn't able to be there to see that. But anyway, I thought I would just highlight his accomplishment. Incidentally, a preliminary version of this paper is available on archives. So if anyone is interested to look at it, there's a QR code there that you can use. I think you put the QR code on the final slide as well, if I remember correctly. Oh, yeah. So before I go further, so the topic on which he's been examining is basically enhancing electricity system resilience. And to do this, he applied adaptive robust optimization. And then conformal prediction is basically a methodology or an approach to characterizing uncertainty around events that can affect electricity supply. There we go. Okay. So so the motivating example that oops, trying to move this out of the way. Okay. So the motivating example that Shuyi is giving, actually during spring of this year, there was so technically it was not a derecho because the weather event didn't satisfy all 5 of the criteria for what defines a derecho. It satisfied 4 out of 5 of them. But a derecho is basically is kind of a catastrophic weather event with extremely high wind, usually thunderstorms, lightning storms, and it just has a catastrophic effect on infrastructure. Anything that is not tied to the ground is basically uprooted. Even things that are tied to the ground, in a lot of cases, end up being uprooted. So to give a timeline here, the weather event actually occurred April 30th. Just in our city of Pittsburgh, which has the city proper has a population of like 600,000 people. There were, close to 200,000 outages, so close to a third of customers lost electricity supply during this event. And as I said, even things that are connected to the ground, like trees, get pulled out of the ground by the wind. 12 hours later, not even half of the outages had been restored. There were 400 electrical crews on the ground that were trying to restore service. And again, this is just focusing on this small city of Pittsburgh, so not the broader Western and Central Pennsylvania region. 24 hours later, there were still folks experiencing outages. And if I remember correctly, in extreme case, there were some customers that took over 1 week to get electricity service restored. And the thing to stress about this is a fairly densely populated urban region. This is not like people who are, living 30 miles away from a substation or something like that. Now, a counterpoint to this, so Shuyi lives, the student Shuyi lives in this region of Pittsburgh, and I think in part because there are some hospitals close to where he lives, there was some basically you could characterize it as hardening of the local utility infrastructure around where he lived. And so he did not experience any outage or electricity supply disruption. So he had completely opposite experience compared to other customers who were impacted. And then he has here some more examples of these types of weather events that hit different parts of North America and have similar types of effects. So these types of events are very common in the Southeast. This was a hurricane event from a few years ago that hit Florida. So, here as the Chiron said, in the aftermath of this hurricane, 16 people were dead and 2 million plus people were left without power after the hurricane hit. And in this case, the local utility, Florida Power and Light, basically said that, they observed that proactively undergrounded power lines performed about 5 to 14 times better than their overhead counterparts during the 2024 hurricane season. So this is just to kind of give some context to what it is that he examined. So these pictures are just other examples of these types of catastrophic weather events. Okay, so what he was looking at was basically, what he was wanting to look at is how to incorporate in a coherent manner and co-optimize reactive response and proactive action. So in this context, reactive response is some sort of measure that is taken ex post after an event to restore service as quickly as possible. So, the classic example, of course, is dispatching repair crews to repair lines after a storm, but you could have other things like mobile generators or mobile batteries or things like that you could deploy. And then proactive actions, these are things that are done ex ante before disasters, basically to reduce the likelihood or severity of future outages. So he gives some examples here, like in the FPL example, undergrounding power lines. If this is too expensive to do, you could, in theory, for example, harden overground infrastructure. So like replacing wooden poles with concrete or composite materials. The thing on the right is something we're very bad at doing in North America, vegetation management, in part because when utilities try to do vegetation management, they usually end up with property owners who come out to the house with a gun and try to scare the person away. So it does make that type of proactive action a little bit more challenging. Okay, so how do we approach the problem? So we start off with the view of let me just. Okay, so we start off. This would be a simple, let's say, two-step or two-stage approach. This is kind of a classic or traditional robust optimization approach. So what you essentially do is you structure a problem as being a two-level optimization. And what you are doing is at the upper or the outer layer, you as in this case, utility, are basically determining proactive actions. So that's represented by this decision variable vector X. And in the lower inner layer, you have nature basically choosing the worst case reactive action. And that's characterized by this level here, where nature is choosing this decision variable vector U, which represents a pattern of outages. And whereas you as the utility investor are trying to minimize this cost associated with disruptions, nature is trying to choose the most disruptive set of outages. So it's trying to maximize this objective here. And then you can have constraints, for example, budget or resource constraints on what the utility is doing at the upper or at the outer level. And then here, this is usually characterized as an ambiguity set or something like that. This is basically a bound or a limit on what you consider as being a reasonable or a plausible set of pattern of outages that could occur. So what is missing here is that this is just looking at the ex ante proactive decisions. And so what he did, and I'll skip through these animations and just show the formulation. So what he did was basically add in this third layer at the bottom, which basically represents the opportunity of the utility to take reactive actions. And so,
actions.
pardon me?
The ex post actions.
These are the ex post actions here, exactly. So this is now a decision variable vector y, and so these are taken after the pattern of outages here are observed, and so so we now have this now third layer inside of the now tri-level model structure. And then what we notice is that before the objective function was basically a cost coefficient on an outage, U, which is a variable basically representing whether nature decides to disrupt or cause a disruption in a region. And then 1 minus X, this is basically the protective action that is being taken ex ante. So what's being changed here is now when we add the reaction here, we get a 1 minus Y term, because the 1 minus Y term is basically representing a reactive step, preventing a disruption from happening. Okay, so this three-level structure here, this now gives you what you would characterize as an adaptive, robust optimization problem. Because before, when we didn't have this here, we were just doing things proactively, taking into consideration the worst case outcome. Now we're doing things proactively, taking into consideration the worst case outcome, but also accounting for the fact that you do have some recourse opportunity after this worst case outcome is realized. Now, one thing that we noticed, or one thing that Shuyi noticed when he first started tackling this problem, is the structure of this objective function is a little bit, it's slightly trickier than what you see in a lot of the robust optimization and adaptive robust optimization literature, because in most cases, people have objective function structures where the variables from the three levels of the problem are additively separable. He doesn't have that structure here, so basically all of the variables are multiplied by one another, so you get these basically bilinear and trilinear terms. As we know, multiplying variables together makes life a little bit more difficult, but because of the special structure of this problem, he's actually able to solve the problem fairly easily. So, I mean, at a high level, he does what most people do when you have these bi or tri-level structures. You just use tricks to basically convert the tri-level into a bi-level, and then use more tricks to convert the bi-level into a single level problem. And so that's effectively what he did. And so, in a nutshell, what he does is, for the lowest level problem, so this inner level problem, where the recourse decisions are being made, you either do one of two things. So if the if this constraint set, if this resource or this budget constraint set on Y has a certain structure in it, then you can basically show that the you can show that this inner level problem is equivalent to its continuous relaxation. So you can relax the binary 0, 1 restrictions on Y. There's some specific structure that you need on the constraint for that to work. Otherwise, you just relax otherwise, if you don't have that structure, well, what you can do is you can basically relax the binary restriction. That means you don't get an exact solution, but you get a solution within some level of tolerance. And then once you've done that, then you can basically collapse the bottom and the middle layer of the problem. So you can basically collapse these into a single problem. The easiest way to do it, which is what he did, is you basically just you use the strong duality theorem to turn this min into a max. And so then once these directions of optimization are aligned, then you just turn that into a min and then combine max problem here.
So Ramteen, the relaxation is not exact, right? So the result.
This relaxation is exact if this budget constraint satisfies certain conditions. So basically, if the budget constraint is totally unimodular, then
Yeah, if it's unimodular,
then
then
this is exact.
Okay, cool.
Let's see. Okay, so sorry, what I skipped over here is so he did attempt to basically use KKT conditions as a way to solve as an alternative way to solve this problem. Long story short, it's very computationally expensive to do it that way, so we didn't actually do that in the end, but he included this just to show that we did try different approaches to solve the problem. What we did instead was so once we transformed the tri-level problem into this two-level min-max problem, then he used Bender's decomposition to basically solve the resultant problem. And so this is giving the Bender's decomposition formulation here. And so basically, to go through quickly, the structure here is you have a master problem where the outer level variables, those are the x's, these are the proactive ex-ante decisions are being determined. So you put in this budget constraint here. This budget constraint is basically, sorry to keep going back and forth, but this budget constraint is basically this constraint here in this feasible set. And then, and then you have here this collection of Bender's optimality cuts, and these you basically generate from solving this subproblem here. The objective of this master problem is just to minimize this auxiliary variable theta. Theta basically represents what the master problem estimate of the subproblem objective function is. And once you have solved the master problem, you get a candidate value for x. You then solve the subproblem. This basically has the objective and the constraints for the recourse problem, which is basically, so this is basically the objective and constraints for this portion of the problem once you have used strong duality to convert this min to a max. So that's this here. This is your objective. This is, so these basically are the dual constraints from the dual of the bottom level of the problem. And then these here are the, I'll talk about these more in a minute. These are basically the These are the constraints that define the ambiguity set. These are basically the restrictions on what is the plausible set of possible outcomes that vector U, which is nature's choosing the worst case scenario with respect to outages or supply disruptions. And so then, as usual, you basically iterate between this master and subproblem as you need to. You separate these Bender's optimality cuts, you add them back up here, and you keep going back and forth until you get convergence between the subproblem and the master problem. This, as I said, so he compared basically doing this Bender's decomposition approach to doing another kind of standard trick for solving these bi-level problems, which is to use KKT conditions. And what he's basically demonstrating here is the size of the problems that you solve doing Bender's decomposition versus doing the KKT condition trick. The problem sizes are much smaller, and so this scales much better as compared to this technique here. And in these expressions for the number of variables, number of constraints, these are basically the n is the number of regions in the system that you're examining. Okay. So the other piece, or the other kind of focus of the work that that Shuyu was doing was basically how to generate predictions of what outage patterns might look like. And so, sorry. So what this is showing as an example data that he collected from in the US, we call these nor'easters. So these are basically winter storms combined with a lot of moisture that comes off of the Atlantic coast. And so this is showing eastern Massachusetts, and what you are seeing is basically so the shading is giving an indication of the severity of the weather condition. The darker the shading is, the more severe the weather is. And then these circles that are popping up are basically indicating the pattern of outages that occur after this winter storm event occurred. And so I mean, there are a couple things that you observe. One is, of course, that the pattern and the severity of the outages is not uniform across the region. But the other is that, so I mean, if you pay attention to the time and the date up here, there is usually a bit of a lag between when the weather comes and when the outages actually occur. Because in a lot of cases, what you are experiencing is you get a lot of precipitation that basically, so it takes time for the precipitation to basically penetrate the surface of the ground. As the ground gets moist, then that basically weakens structures and trees and things like that. And so then they start toppling, so on and so forth. So as is illustrated here, and you see this in a lot of these other types of especially winter weather effects, there's usually there can be a 12-hour, 24-hour lag between when the weather event is most severe and when the effects are actually felt in terms of disrupting the infrastructure. Okay. So in terms of,
but does it impact the problem that there is such a delay?
So not in the formulation that we had, but for other follow-on work that we're doing, it will, yeah.
Okay.
because like we have been examining follow-on work where instead of so to go back here, so we have been examining follow-on work when so for example, instead of this just being a single shot resource allocation problem, exactly, you have like a dynamic sequence of resource allocation, and so you have to think about not only where, but also when you're going to allocate these scarce resources after a weather event occurs. And so if you know that there might be a 12-hour lag between when the weather event occurs and when the disruption is going to be experienced, that could, in theory, affect how you're going to use those resources. Okay, so in terms of constructing the uncertainty set, so just sorry to keep going back and forth, but just to emphasize. So really the focus here now is on how do you construct the constraints in the middle level of this tri-level optimization. And so the trade-off is that if you make this set that I'm calling script U, if you make it too big, then you end up with decisions that are overly conservative because you're basically protecting yourself against extremely unlikely but very high consequence events. On the other hand, if you make the set too small, then you're going to, in some sense, be overly confident or overly optimistic in terms of what happens. And so the trade-off is basically how you kind of hit that sweet spot where you're not being overly conservative, but at the same time, you're not being overly Pollyannish that nothing bad is going to happen. And so we examined this idea of using conformal prediction. And so what this visual is indicating is so this is just giving an example. If you have two different regions, so the approach that we're taking is we're basically generating conformal prediction bounds on the extent of outages for individual regions, but then we also add a pair of global constraints on the pattern of outages globally across all of the regions. And so what you end up with, I want to.
Sorry, why you're adding the second constraint, the global constraints? Is it geographical constraints, right?
Yeah, so the idea of the global constraint is you're basically accounting for spatial correlation in the pattern of outages. So the one way to think about it is the horizontal and the vertical bounds. These are basically the per region bounds on the extent of outages, and then the diagonal bound is giving you a bound globally on the extent of outages. And so I thought he put it in here, but he did produce a table that basically shows what the trade-off is in terms of the size of the ambiguity set that you get versus the theoretical coverage probability. So what is the probability with which an outage event is actually going to be inside of the ambiguity set that you define? And so basically what he's able to show is that generating the bounds in this way, you get a good trade-off between the size of the set that you get versus the coverage probability. And you must have dropped that. from these slides that he prepared. So the last thing here before I go through a handful of results is he compares he compared basically what his tri-level model does to two other baselines. So one is basically just optimizing the proactive actions without consideration of the reactive actions. So the objective function has a similar structure to what I had before. You still have the cost of disruption to each region and the 1 minus x term, which basically captures the fact that if you take proactive action, you basically prevent an outage from occurring. But here, instead of having a lower level choice of U being optimized, there's just a deterministic forecast of outage patterns. So that's what we're calling U hat here. And then down here, this is a slightly, you might argue, a slightly more intelligent variant of this. So here you're basically now co-optimizing the proactive and the reactive actions. U hat is still this deterministic forecast of a pattern of outages. And so you have the 1 minus x, 1 minus y switches in the objective function there. Okay, so just to summarize a few set of results here. So this is looking at varying the reactive budgets. So this is varying how much resource you have in terms of like crews or resources that you can deploy after an outage occurs. And so this is showing the percentage difference in the objective function you get either by doing this, which is proactive only, or this, which is co-optimized proactive and reactive. So so this is the percentage difference in the cost between either proactive only or proactive and reactive compared to the tri-level model that she developed. And so as we expect, there are kind of two things that we see. One is, of course, that the proactive and the co-optimized don't work as well as the tri-level approach, where you're taking into account the range of possible worst case outcomes. But what you notice is that as the reactive budget increases, the performance gap between these simpler methods and the tri-level model shrinks. And the reason is that as the reactive budget increases, so if you have more and more crews, you have more and more material to use ex post, then the quality of the ex ante decisions that you make is not as important, right? You have more resources with which to react, so making good proactive decisions is not as important. Let me see. This is so this here is varying the instead of varying the reactive budget, this is varying the proactive budget. So here we get kind of a mixed effect. So basically, at this end here, if your proactive budget is very limited, you're so constrained that doing tri-level optimization as opposed to deterministic optimization is not really going to make much of a difference because you don't have a lot of resources with which to work. At the opposite extreme, if your proactive budget is very high, then because the resources are not scarce, optimizing is not as important. So it's here in the middle where you have some resources with which to work. You don't have so much that the quality of the decisions is not important. This is where you get the performance benefit between, you get the performance benefit from using the tri-level approach. These figures are just summarizing the solution time from using the Bender's decomposition approach as opposed to using the other standard trick, which is converting the bi-level problem to a single level problem using KKT conditions, and then comparing that to what he's calling brute force, which is essentially just explicit enumeration. And so as you increase the number of regions into which you've subdivided the network, the solution times for the KKT approach and the brute force approach increase. For Bender's decomposition remains relatively flat. So in terms of solution time, the Bender's decomposition works relatively well. And this is just summarizing the optimality gaps of the solutions that you get. So the methods are fairly close to exact, subject to basically numerical rounding errors. The last thing that he did was, so he also examined the case study based off of that nor'eastern event that hit Massachusetts. So I won't go into the details of this, but he basically just examines what the tri-level model would do as opposed to what just deterministic approach would do in terms of where the proactive actions are taken and then what the reactive actions look like. And so to summarize, jointly considering reactive and proactive actions results in, let's say, improved decisions with respect to enhancing the resilience of electricity systems. As I said, that does depend to some extent on how much resources you have available. If your resource constraints are very tight or they're very loose, then the quality of the decisions that you make may not be as important because either you're overly constrained, you can't do anything, or if you have so much resource, then it doesn't really matter. The other thing to emphasize is we found that the solution technique using Bender's decomposition to solve the two-level problem after you convert the tri-level to the bi-level version of the model works quite well. It scales quite well compared to the other kind of standard techniques people use to solve these types of problems. And then finally, I didn't include the lemma, which is in the archive paper. So there are some formal guarantees on the predictions or the uncertainty sets that the conformal predictions provide. So basically, subject to an exchangeability assumption on the data, you can basically guarantee that the uncertainty sets satisfy whatever your desired coverage probability is. So if you want to generate, what that means is if you want to generate an uncertainty set such that vector U, which is that's the 0, 1 vector that tells you where disruptions are going to occur. So if you want to construct an uncertainty set that U is guaranteed to be in that set with, probability at least 95%. The way that we generate the the way that we generate the uncertainty sets is basically guaranteed to meet that coverage probability. And so that's just a nice theoretical property as far as the predictive approach is concerned. As I said before, there's a QR code there if you'd like to see the archive version of the paper, which provides a lot more detail. And of course, if you have questions, since Shuyi actually did the work, he is going to be, he'll do a much better job of answering questions than I can attempt to, but I'll try anyway for the next few minutes.
Cool. Fantastic. Let's go first with the questions here in person. Is there any question here? No, I have many.
Yeah. Can you explain a bit? So this you had, right? I mean, you have the on the benchmark models. So is it like the worst disruption, or the ones that you compare with
So you're asking about
this?
these U-hats here?
Yeah.
Yeah, so we generated U-hats in a few different ways. So one was one was we used the mean from the historical data. And so let me back up one moment. So when I'm talking about historical data, so our assumption going into construction of the uncertainty sets is that we have a historical data set that we can use. We have historical outage data, and we're basically going to use those historical data to try to generate uncertainty sets. And so from those historical data, we basically get the local and the global constraints, which are illustrated by the lines in the figure here, which give us this polyhedral uncertainty set from the conformal prediction.
I think
Now
should be one of the vertexes, right?
Say it again.
You had, which the outage that the nature chooses us to be the worst case, it should be one of the vertexes.
Well, so in comparing what the tri-level model does to, for example, this deterministic version here. So we generated U-hat in a few different ways. So one was we just set U-hat to the historical mean from this data set. Another was historical mean minus 1 or 2 standard deviations. I think it was 2 standard deviations. So that was basically supposed to be, no, not 2, 1 point, basically a 95% confidence interval. So, and then the third way was we just trained a predictive model to the historical data, and we just used the output of the historical, so the trained model.
And that would be the worst disruption. The output of this predicted of this trained model would be the or
well, when you put so for example, if you put U-hat just equal to the historical mean, I mean I wouldn't call that a worst case. So you're basically projecting against an average outcome. If you set U-hat to mean minus whatever it is, 1.6 times the standard deviation, you're protecting against what you think is a 95% confidence interval on a worst case. And so we basically examined, what is the range of deterministic predictions that you could put in here, and how does that do compared to using the conformal prediction?
And then if I may have a follow-up there, because so how is in the tri-level, right? Because you have the max U there. Is this dependent on the rest of the variables, or is it maybe, can I not just do some kind of exactly what you did with historical data, just pick the worst U? Why should I have that in my tri-level problem? Where's the dependency? Maybe I missed something, but
So your question was how the U reacts to the decisions that the planner makes?
But I react to you, right? I react, so both my proactive and reactive decisions are dependent on the worst case U. That's the way I understand it.
Yeah, so in this structure, I mean,
why is U a variable?
In this structure, U is reacting in some sense to X, right? Because suppose that I have, just as an example, suppose I have two regions. So if I set X equal to 1 in this region, meaning I have protected this region,
then another U will.
Then U is not going to choose to attack this region. It's going to choose to attack the other one. So you're correct. I mean, there is an assumption here that nature is going to be adversarial. So it is subject to still having to live within the uncertainty set that you've generated using historical data. It is going to choose a pattern of U's that react to the X's that you've chosen. And conversely, you are going to choose X anticipating how U is going to react to your choice.
Okay. Yeah.
So yeah, it is, I mean, strictly speaking, if you think that, I mean, strictly speaking, you can argue that maybe this is a tenuous assumption because we're basically saying that phenomena that are intrinsically just driven by randomness are in some sense reacting to decisions that you make. I mean, if this is truly random, then you might argue that we're being overly pessimistic because we're saying that a hurricane or we're saying that a derecho is going to target parts of the network that have X equal to 0, they're not protected. And so you might argue that's being overly pessimistic, which is, I mean, it's a fair criticism, but that also comes with that comes with this approach of trying to choose decisions that are robust to possible outcomes.
Good. Any question here?
I maybe have a follow-up question. So
Can you speak up loudly?
yeah, so basically the uncertainty set the ambiguity set are based on the conformal prediction,
Mhm.
right? But what I'm missing is, do you have a model, like to model the disruption versus like the weather realization? That's what I'm missing. How you build the conformal prediction sets.
Yeah, so yeah, I skipped over this detail. So to generate and you can find the details of this in the paper. So basically, to generate these bounds here, so the bounds here are written as functions of a set of features that I'm calling W. So these features W, so in the simple example that I showed here, so this example was just with data that we generated. So basically, the features W are just weather variables that we generated, and then the assumption is basically just weather variables are driving outages. Now for this case study here, we have some additional data, not just about weather variables, but we had data about the age of infrastructure in the different counties in Massachusetts. So we had that plus some demographic information like population density, so on and so forth, to basically determine we included those in the model because to some extent they may drive the propensity for outages to occur, in urban versus rural areas or areas with newer as opposed to older infrastructure, so on and so forth.
Well, Let me check with online participants if there is any question online, and if so, please feel free to unmute and ask your question. So maybe not. Maybe I can ask the last. Very quick. No, maybe I can ask the last one. So can we implicitly assuming that the future outages will follow the traditional outages? But if, I don't know, for any reason, climate change or whatever, something, a totally new pattern of outage happens, will our model work or not? Maybe not.
Yeah, no, that's certainly another fair criticism. So the way that we generated these predictions is basically premised on the assumption that historical outage patterns are a good proxy or good predictor of future outage patterns. So if that's not a good assumption, then of course that will basically cause the predictive power of the uncertainty bounds to fall apart.
Then shall we just enlarge the uncertainty set, or no? We should try to find another technique,
Well, so in theory, you could just enlarge the uncertainty set. You could, I could see, for example, you could try to, so if you have historical data that gives you some relationship between weather features and patterns of outages, you could still use those data, but when you're predicting future outages, you basically have to account for the fact that weather conditions could be much more extreme than they are in the historical data. So in the historical data, you may only have observations with whatever 1 meter of snowfall or 10 meter per second wind speed, and maybe you predict, because the climate's changing, that in the future wind speeds could be 20 meters per second. And so you basically use those, you simulate future weather conditions, taking into account how the changing climate can basically change that, and then you see how that's going to change your predictions. Now, of course, the limitation there is that if you've only seen outages when the wind speed is 10 meters per second, you can't necessarily extrapolate what is going to happen if the wind speed goes to 20 meters per second. So does that double the outage risk, or is there a hockey stick shape, or does it asymptote at some point once the wind speed is high enough, then it's reached maximum destructiveness? So that piece you wouldn't be able to predict, unfortunately.
Thank you so much.